Today, we're basically putting on our detective hats to unravel the hidden physics happening all around us, every single second. We're talking everything from the simple act of pedaling a bicycle down the street to the massive, invisible pull of the entire universe that keeps our feet planted firmly on the ground. We're decoding the fundamental rules of motion today, drawing directly from the essential concepts of the Class 9 physics syllabus. So let's dive right in. Here is our roadmap for the day. We'll kick things off with an introduction to force, compare contact versus non-contact forces, explore Newton's laws of motion, look at the universal law of gravitation, and then finish up with mass versus weight. Section 1. Introduction to force. Let's start with the ultimate mover of things. Think about this for a second. What exactly is it that pushes a cyclist forward when they want to speed up? Or what allows a baker to take a lump of dough and knead it into a totally different shape? What's the common denominator here? Well, the answer is force. Force is simply that external agent doing all the heavy lifting. It's the thing that shifts a carom board striker from sitting totally still into rapid motion with just a quick flick of your finger. It's what stops a moving object in its tracks. And for non-rigid things, like a sponge, a tube of toothpaste, or that baker's dough, force is what actually changes their shape and size when you compress or push them. Moving right along to Section 2, contact versus non-contact forces. So all the pushes and pulls in the universe basically fall into two broad categories. On one side, we've got contact forces, which, just like it sounds, require actual physical touch. On the other side, we have non-contact forces. These are those invisible forces that act across a distance without any physical connection whatsoever. Let's break down those contact forces first, because when things actually touch, physics happens. We see friction working against the soles of our shoes when we walk. There's normal reaction, which is literally just a table pushing upward on a book so it doesn't fall right through. Then you've got tension, like the force in a taut string holding up a pendulum, restoring forces that snap a stretched rubber band right back to its original shape, and collision, the intense force when two things, like a couple of rolling balls, just crash into each other and bounce away. On the flip side, without any touching at all, we have non-contact forces. Gravitational force is what pulls a falling apple straight down to the earth. Electrostatic force is that crazy static electricity you see when a plastic comb miraculously picks up tiny bits of paper. And magnetic force is exactly why your fridge door snaps tightly shut, or why your wireless earbuds stick together. They pull or push across a distance. Okay, Section 3, Newton's laws of motion. Let's decode the 3 universal rules discovered by the absolute legend who watched an apple fall. Have you ever wondered why your body violently jerks backward when a bus you're standing on suddenly accelerates forward? Or, kind of similarly, why beating a dusty carpet with a stick magically forces the dust out of it? The answer to both of these mysteries is Newton's first law, inertia of rest. Basically, an object at rest really stubbornly wants to stay at rest. When you're on that bus, your feet are in contact with the floor and move forward with it. But your upper body, it has inertia. It wants to stay exactly where it was in the air, so it feels like you're falling backward. Same deal applies to the carpet. You move the carpet violently, but the dust tries to stay put, effectively separating itself from the fabric. And this relates directly to mass. Like the quote says, an elephant has way more inertia than a mouse. Mass is the true measure of inertia. You could easily push a bicycle to get it moving, right? But try pushing a massive truck with your bare hands. No way. It's nearly impossible because the truck's huge mass means it has massive inertia. It stubbornly resists any change to its state of rest. Which brings us to Newton's second law. This is where we mathematically define force. We look at a concept called momentum, which is just an object's mass multiplied by its velocity. If you calculate the difference between the final momentum and the initial momentum, and then divide that by the time it took to change, you get the rate of change of momentum. And that gives you the exact amount of force applied. So, force equals mass times acceleration. Let's actually put this into perspective. Think about a high-speed game of cricket. Why do fielders purposefully pull their hands backward, bringing the ball down toward their chest during a catch, instead of just keeping their hands rigidly stuck out in front? It's pure physics keeping them from getting hurt. By pulling their hands back, they're consciously increasing the time it takes to completely stop the ball. Mathematically speaking, if you increase the time, you decrease the rate of change of momentum. A lower rate of change means a much smaller force impacting the hands. More time equals less force, which equals no broken fingers. It's the exact same reason a glass dropped on a soft carpet might bounce, but absolutely shatters on a hard tile floor. The carpet extends the time of impact. And finally, we reach Newton's third law. For every action, there is an equal and opposite reaction. If you've ever stepped out of a small rowing boat onto the shore, you've definitely experienced this. Your action is pushing forward off the boat, but your feet push the boat with an equal and opposite reaction, sending the boat drifting backward into the water. Two distinct bodies, two distinct forces. All right, section 4, universal law of gravitation. Let's zoom way out from the cricket pitch to the entire universe. What's really fascinating here is that gravity isn't just an Earth thing. Every single particle in the universe attracts every other particle. Technically, you are pulling on a mango in a tree right now, and that mango is pulling right back on you. The only reason you don't fly towards each other is that your masses are tiny compared to the massive Earth pulling you both down. The exact math for this cosmic attraction involves this tiny, super important number, 6.67 times 10 to the power of negative 11. This is the universal gravitational constant, or capital G. It's the baseline rule of attraction that applies perfectly whether you're measuring the pull between two rocks on the ground or the pull between the sun and Jupiter. But when we talk specifically about an object in free fall being pulled toward Earth, we use a different value, small g, the acceleration due to Earth's gravity. That value is exactly 9.8 meters per second squared. This means for every single second an object falls toward the Earth, its speed increases by 9.8 meters per second. It just gets faster and faster the longer it falls. And finally, we arrive at section 5, mass versus weight. Let's clear this up once and for all. Mass and weight are absolutely not the same thing. Mass is simply the amount of matter packed inside an object. It's measured in kilograms, and the crucial point is it never ever changes. Whether you are standing in Kashmir or floating around on the moon, your mass remains exactly the same. Weight, on the other hand, is not a measure of matter. Weight is actually a force. It's calculated as your mass multiplied by gravity. Because it's a force pulling you down, it's measured in newtons. And because gravitational pull changes depending on where you are, your weight changes depending on your location, even though your mass stays perfectly constant. We've covered a ton of ground in this explainer today, from the friction under our shoes to the massive gravitational constants of the cosmos. So knowing that physics governs everything from a dusty carpet to falling meteors, I want to leave you with this. What other hidden forces are pulling, pushing, and reacting around you right this very second? Take a look around the room you're in and see if you can spot the invisible mechanics of the universe at play. Thanks for joining.